G'day guys, Mac with the S Circle. I know so many of you are going to be stuck at home with this virus going around. I don't want to do a video today about Warhammer. I want to talk about something completely different. And that is more to do with my real life skill set and job. So, for those who don't know, I'm a mechanical engineer trade side, so not a bachelor. Which means that I went to a trade school, learned how to become a fitter and turner. How to use machines like lathes, mills, that kind of thing, precision measurement, and then eventually went back and did more education, more schooling, and went up a few levels again. So at this point, obviously, I have a pretty broad skill set, including electrical stuff, as well as specialising in things like firearms and hydraulics, and working in plastic injection moulding industry at the moment, recycling plastics. I've done heaps of metal work. And the question was posed a little while back, and that was, what level of technology could I bring to, say, a time period? So if I was sent back in time, with the knowledge I have now, what could I do? And actually the answer is a surprisingly large amount. And I thought I would try and just do a sort of podcast episode and explain what I would do, the approach I would take. And a few things to consider in the hypothetical perfect best case scenario. So first things first, if I'm sent back to pre-Iron Age, I'm going to have a very difficult time. Because iron and steel, obviously refined iron essentially, where you're controlling the carbon content, I can do a lot with that. If you've already got iron, and especially if you've already got steel in your society, fantastic, things are very easy for me. If your society hasn't got to that point, my first step is basically to get your society to that point. Now, once I've got there, well, okay, first, how are we going to get from bronze to steel or iron? Essentially, you've got to get the temperatures up when you're melting your raw ingredients, your iron ore, which means you have to build much better furnaces. Have to get those temperatures right up there, because melting something like copper, say 600 degrees Celsius, give or take, compared to melting iron at 1800 degrees Celsius, give or take, that's quite a difficult process. Not only that, you've got to be able to get rid of impurities, that kind of thing. It's a whole process in and of itself. So my basis here is going to be, let's pretend we're starting in an Iron Age society. Now, can I understand them and can they understand me? Well, that's obviously going to be the biggest hurdle. Anything back to maybe Old English can work. I can work with that. However, that's European languages. I'd be stuffed if I ended up in, say, China, Mongolia, Japan, India, anywhere in Africa or the Americas. So you're probably looking at some sort of anglicised country. But let's ignore those inconvenient parts of this exercise, and let's just say the society I end up with, they have iron, they have small amounts of steel, and they can understand me. And they're willing to understand me. What can I do now? Well, the first things first, the most important thing to do is I have to create an accurate measuring system. Because if you want to make anything precise, you need to be able to measure things. Now, how am I going to make an accurate measuring tool? Well, I need to make the one machine that can make everything and anything. And that's a lathe. So, I'm going to have to use a little bit of nous here, but essentially, I would probably try and find a water wheel to power my lathe. It'll be a wooden lathe to start with. This wooden lathe, turned by just a big paddle wheel being turned by a river, will be what I use to create my very bare bones essential lathe. Now, I've built a lathe from scratch before. It was a wood turning lathe. I understand how to make pulleys, how to grind and sharpen my tools, that kind of thing. So, with these small amounts of steel available to me, I'll be able to create steel tools that are able to cut other steels and make my lathe work. I know the angles are required for this, therefore I can do things like creating the first threads. Now, I can't create a thread until I've cut some gears. So one of the things I'm going to do is use calipers and geometry, and I'm going to find out, I'm going to draw up some circles to create some gears, and I'm going to find out my pitch between my teeth by using the calipers. I can divide up a circle into an equal number of points. Now, how am I going to measure those points? Well, I need to know what a meter is. I pick a meter because meter is very easy to work out. Because what I can do with it is I can use simple angles in order to figure it out. So, my first exercise here, I'm going to figure out how to measure millimeters, centimeters, and kilometers straight off the bat. Now, this is pretty easily done. Believe it or not, this is true, and it all involves geometry and the circle again. My known height is 175 centimeters. So I will take my height, I can just mark it out on the ground, on a stick, something like that. Preferably on something that's not going to be affected too much by changes in temperature, that kind of thing, because it's going to skew my measurements later. I mark out my 175 centimeter length on this object. I can then break it up into 175 even increments using calipers. Once I've done this, I've got the centimeter. And then what I can do is I can then make the millimeter by dividing each of those into 10. I can find out the kilometer by taking a circle, dividing into 6,400 sections. This is actually far quicker and easier than you think. All you have to do is essentially make your first 4 90-degree dimensions. Again, simple geometry. You can do this with just a pair of calipers by using dimensions taken off the radius. Anyway, I'm babbling here. Once we have 6,400 different degrees called mils in our circle, if I then extrapolate that out at a distance of 1 kilometer, the difference between two of those points will be 1 meter. And so I can actually check my dimensions and my measuring system by cross-referencing these things against one another. So I've now got a basic accurate measuring system in millimeters. Now I'm choosing millimeters because metric works off units of tens and hundreds, and it's very easy to work with as opposed to imperial, where the fractional system can create some problems. It's a good system, but it's a different system. Being able to add, subtract, multiply everything by tens will make it very easy to pass this knowledge on to others. So I've got the metric system. Great. It's a very basic version of it. Of course, we can figure out kilos and that kind of thing using litre of water, but neither here nor there. So now I've got this system in place. I can use this in order to measure out the different sizes of gears. I can then put these gears together in order to create the first thread. Now, by machining a thread, by the way, I'll cut these gears the way I did it in trade school. Drilling it by hand, using a saw to cut the teeth out, and using a file to finish it. It's tedious and will take several days before I have enough gears to assemble a functional lathe. But by using the basic wood lathe, running in our water mill, being turned by the river, and combining it with these gears, I will be able to make steel parts, and using these, I'll be able to create accurate threads. Now, threads are something you take for granted in modern society. I know I do, even though I know the work that goes into creating them. But every screw, nut, bolt you see is a standard size these days. That wasn't the case 250 years ago. It wasn't until a guy named Whitworth came along and standardized these things. Before that, everything was made custom. Well, what I can do is, straight off the bat, start to create things that are a certain size. And of course, once you start making accurate threads and accurate measuring tools, well, you can now create more accurate lathes and more accurate milling machines. And with each generation, what you create will get more and more accurate. Now, this is fantastic, because within probably the first 2 years, I've gone from a lathe that is poorly measuring 1/10 of a millimeter to something that will be able to machine down to 1/100th of a millimeter. But it will take time, and it will basically consume my entire efforts for that first year is making a lathe and making accurate ways of measuring on it. Specifically, the thread comes into play here, because if I know the distance that a thread travels in one rotation, what I can do is then use that knowledge that I know in order to calculate the distance between a hammer and an anvil. And what I'm creating here, when I say a hammer and an anvil, I'm talking about a fixed and a moving part of a measuring device called a micrometer. I can have a fixed measurement surface, and I put it on one side of an object like a shaft. I then wind the bolt in on the other side, and if I know how many turns I've done of that bolt and divide it up accurately, I will then get an accurate measurement of the shaft that I'm now measuring. Because the bolt will have moved a certain distance, that tells me the size of the object. This is crucial fundamental stuff. It's the most important part of any engineering. We've got to be able to measure it. So I've now created the basic lathe, and I've created the basic micrometer. And I will now have to refine these things for probably 2 or 3 years before I get some really accurate measuring tools. But now that I have an accurate lathe, an accurate milling machine, and accurate measuring tools, I can now start to reproduce these machines and make lots of lathes and mills and accurate measuring tools. Now I'm starting to get the basics of industry. What I can also do is start producing more things in steel, which means bigger and more powerful furnaces, and understanding how to make these furnaces in large scale. Now, thanks to my modern knowledge, I know how to do this, but the best way is with electricity. So, how are we going to get electricity? Well, we've got to start out basic. What we're going to do is we're going to try and create a steam turbine. Now, there's many ways that you could go about it. You could create steam triple expansion engines, for example, but I'm going to pick the turbine because it's more modern tech, but it is still relatively simple in concept, just hard to execute. A turbine is essentially a long shaft with many fins, multiple rows of them from end to end. It's not just one big fan blade, it's dozens of big fan blades. And we want to pass superheated steam through this. Now, this isn't steam like comes out your kettle. This is the sort of steam that might be many hundreds of degrees Celsius hot. It's so hot that it's no longer really water vapor, it's something else entirely, for the purposes of this discussion anyway. So, how am I going to get water that hot? I need to create boilers. So, boilers are essentially a pressurized vessel that you can heat water in and get this steam up to a high level. And boilers are very dangerous if constructed incorrectly. So what I need to do is have a series of tubes that are going to pass through this heated area, giving as much surface area as possible to the water to heat it up. Which means that at some point I'm going to have to figure out how to weld things or get very good at riveting. So we're probably going to start with riveting here because we don't have electricity yet, and although we could probably make basic oxyacetylene, it's still rather difficult at this point in time because we don't really have a way of manufacturing the cylinders yet. So, riveting. We're going to have to make flared pipes that we can place into this boiler, and by passing water through these pipes and heating the outside of these pipes, we're going to heat up the water. So we're going to need dozens, if not hundreds of pipes. How are we going to create these pipes? Well, there are two ways. We can either take a solid piece of steel and drill through it, or what we can do is take a bar of steel and then wrap a red hot strip of steel around it and pattern weld it together into a tube. That would be our starting point. It is not the most efficient way of creating a tube, but it's by far the easiest. So by doing this, we will be able to make a boiler vessel that will be able to take quite some heat. Now again, this is not a super high pressure boiler yet. That's much further down the track. But by passing this superheated steam through a big fan system, our turbine, we are able to now get it to rotate. We now have mechanical force. Okay, I could use this to power my lathes and milling machines directly or through a clutch system. Great. What now? Well, I need to now create electric motors. So how am I going to do this? Well, I'm going to need copper windings, so I'm going to need to make a copper draw line. Now again, it's actually a lot easier than it sounds. I'm going to pass copper wire between two steel wheels that are clamping down towards one another with pressure. This is going to squash the copper and as the copper is pulled through, it's going to make it thinner. And I can pass this through several rollers, and by the time I'm done, I've drawn the copper wire from something that might be 10 millimeters thick, perhaps like a 1/4 inch thick, and draw it right down to 1/32 of an inch thick, something like that, a couple of mils thick at most. I can then take this copper wire and wrap it into windings and use pieces of steel that I can magnetize just through heat. You can magnetize steel by actually putting it into an oven, heating it to a temperature, and then letting it out again. It's not very hot, by the way, to do this. It's quite easy, and we already have furnaces that can make things thousands of degrees because we're producing steel, so this is fantastic. We've now created, by having a steel shaft with magnetized iron blocks around it, and then having a series of copper windings wrapped around iron blocks surrounding that, we've now created a very basic electrical system. And this will actually be giving off, every time those magnets pass around the copper, or the copper I should say passes around these magnets as the shaft spins, what it's going to do is be giving off pulses of electricity. Now, controlling them is not going to be easy at first. You see, we can either have a direct current system or we can have an alternating current system. I'd probably try and stick with direct current because it's going to make powering other things very simple to start with, but of course alternating current has its own benefits. But in order to really get the most out of that, I'm probably going to need transistors of some kind. Again, much further down the track. But if I've now got direct current, I can now use this to start powering things electrically. I can use it to power electrical motors, so I can get more... I can get things like light, so we can work later into the night, have rotating shifts, that kind of thing in my little workshop. I can also use it to power basic things like, say, soldering irons. Because all I need to do is pass an electrical current through a piece of metal, and that piece of metal is going to be heated up by the resistance, and that's going to create heat. That's the basic principle of an incandescent light bulb, which, of course, I know how to make. So, by combining these things together, we've now made lathes, we've now made accurate measuring devices, we've got a standardized system of making screws and nuts and bolts and that kind of thing. We've now moved up to making milling machines as part of the lathe process, taking the same principles, just expanding upon them. We've then gone to making basic boilers and steam turbines. Well, now that I have electricity, I can solder and I can weld. And now I can make much better boilers, which means I can now create things that can take more pressure, more steam, create far better turbines, far more potent amounts of electricity. So by doing this, I've essentially taken a society that could be, we'll say, Roman level of technology. We can take them up to the Industrial Revolution, and it will take about 4 or 5 years. So that's what I think I could do. Now, of course, implementing it is always much harder, but again, like I've said, just using hand tools, I've made gears from scratch. I've made a lathe from scratch, just using another lathe and a milling machine. And the milling machine was only used to make part of the chuck. It wasn't something that I couldn't do by hand, it just did it much faster. So this is all stuff I can make by hand or with very basic machinery. And as I say, the hardest part is having an accurate measurement system. Because I don't need to drill many things, so drills aren't a huge worry if they're not accurate. They could be your local blacksmith made drills of the time period. The biggest thing for me is going to be making decent tooling, decent steels. Now this is another thing, because alloys are going to start to come into play and different ways of combining steels. Now I know how to extract different elements from their different core rocks, like for example aluminium. If I want to get aluminium, I'm going to need bauxite, which is a type of white rock, and this bauxite we're going to need to crush it up, and we're going to need to chemically attack it to draw out the aluminium from the bauxite. We're then going to need to have this chemically attacked broth. We're going to have to pass current through it and place copper sheets into it, which is going to cause all the little particles of aluminium to stick to this copper sheeting. So aluminium is rather difficult material to get out. If I know how to do it, I can therefore pass this knowledge on. I can also pass on Pascal's law. I can pass on hydraulic information. So I can tell them that, in our fluid systems, our hydraulics, that the force is going to be equal and opposite in all directions, for example. And we can start to lay the foundations of basic hydraulics. Now, things like seals. Seals are a huge thing. How are we going to stop the oil from leaking out of the things we create? Well, at first, we're going to have to use leather. Leather is still used even today in seals. It's used in pumps especially. We can use leather to start with, but if we have access to rubber, and I'm talking rubber trees here, we can use natural rubber and learn how to vulcanize it through repetitive action and heating of the rubber. That way we can start to look at things like tires, rubber belts for our machinery that we're making, which is much more durable than leather belts. And by doing this, we can really start to advance the society along. But of course, this isn't the stuff that people actually think of when we bring up this topic, and that's why I thought it would make an interesting video for today, completely different to the normal topics that it is that if you say to someone, if you went back into the past, what would you do? And, I mean, most people probably think, oh, geez, you know, I'm going to really miss what are the modern luxuries of today. But they don't think about, like, even if someone knows how to make something, like, they might know how to make a gun. Right? They might know the principles of how a gun works, but do you know how to make the tooling to make your gun? If you don't know that, you haven't left stage 1. You can't get to stage 2. Because that's another thing. I do know the principles of making firearms, and I know how to make all the machinery and the parts for it. Therefore, I can also take this primitive society, and I probably couldn't, with the technology available, in the time available, get them to the level of repeating firearms, like semi-automatics, namely. But I could probably get them up to black powder revolvers, that kind of thing. I do know that I can make nitrocellulose, but of course I can't guarantee the quality yet because the systems aren't in place of the copper used to make the casings. Also, fulminate of mercury. Yes, I can make that to create primer caps, but again, it's a dangerous process. If I'm the only one who knows this technology, I don't want to go experimenting, showing other people, here's how we make this, and then blow my fingers off and make me kind of useless. Everything I've designed to this point and spoken about are things I can safely create to advance the society, because again, you don't go out and start by saying, hey, I know the principles behind making an atom bomb. You know, we just need a sufficiently dense core of uranium. We're going to shoot it with another piece of uranium, and we're going to use explosive reaction to try and compress these two things together. That's going to work out really badly. So we want to avoid that. But I can take things like gunpowder, for example, and say, okay, here's how we can make a percussion cap. If we pour a tiny little droplet of this fulminate of mercury into this copper capsule here, and then we crimp over the edges and seal it, we can then hit this and it will make a bang. We can then use that to ignite gunpowder or nitrocellulose. But again, don't want to use nitrocellulose. I can say, okay, we can make better barrels, for example, because we can bore them out of solid steel in a lathe, or we can wrap steel again around a tube and pattern weld it, which is the way that old guns were made. But of course, we don't need to rely on the flintlock because we have the percussion cap, so we've advanced the technology quite a lot there. Also, rifling. We can rifle. All we need to do is learn how to broach the barrels. We can make a tool for this. It can be made by hand, but with great difficulty because it's a very hard material. Or we can make the barrels by, we can make the broaches, by turning something and then milling it into size. With our milling machines and our lathes, we can also create carbide tools. This is difficult though, because we're going to need to get a decent amount of tungsten, and we're going to need actual carbon that we can add to the tungsten in the right proportions through trial and error, crush it with immense hydraulic pressure into the pattern of the tool that we want, and then we're going to have to bake it at a couple thousand degrees. So again, this is further on down the line stuff, but once we do that, we can now use very, very hard materials to cut with, which means we can cut even harder steels. When it comes to steels, again, I can greatly advance the metallurgy because we're not just going to be working with steel, which is just iron and carbon to a controlled content. What we're going to be doing is we're going to be adding in things like cobalt, and we're going to be adding things like zinc and creating zinc coatings and electroplating it. We can add chromium in there. We can add some toxic things like that. We maybe could add in molybdenum or vanadium. And by adding these different materials in very small amounts of the steel, we can greatly change its chemical properties. We can create stainless steel, non-magnetic steel. We could create high carbon steels like Bisalloy. We can create tool steels, for example, which is again going to be very important for making drill parts, for making parts for our lathes and milling machines, for cutting other steels. We can also take technologies like the screw propeller. Hey, they haven't got ships yet that are anywhere near having engines. We can explain that if you have an object, its buoyancy is dictated by its displacement. If it displaces more water than it actually weighs, it'll float. Okay, we can now make iron-hulled ships. We know how to rivet them together, but we also have basic welding. Because again, we've got electricity. We can use electricity to TIG weld. We'll need tungsten to do it, but we can do it. So, we can take our screw technology, a long shaft with a propeller on the end, and we can, again, skip a few stages like paddle steamers, and we're going to a much more efficient engine with the turbine and a triple expansion steam engine, and a much better propulsion system going for a screw propeller over a paddle wheel. So there's a lot of good stuff to be had here. We also have more powerful steering systems in that they won't be a little wooden rudder on the back of it being turned by a steering wheel. It'll be a wooden rudder that's being turned by a hydraulic system that is being told what to do by a steering wheel. So the mechanical advantage there is immense. It means we can build larger ships and much faster shipping. This means that you'll be able to get increased trade and get better access to raw goods, so economically you're going to get a huge advantage. And look, to be honest, I go on all day about this subject, but I thought for something different and out the box, this would be something really fun to play with. So I want to hear people's thoughts. Where do you think I've gotten it critically wrong in my analysis? And again, bearing in mind this is the best case scenario where people can understand me and I have some raw material to work with to start with. I mean, I could get dumped in ancient Egypt in 4000 BC or something and really have my work cut out for me, because then I'm working with super primitive materials. It will take some time even to get up to the level of iron casting, but I think this is a pretty fun thought exercise. I guess you could loosely tie it into 40k in some way by saying, what would happen if your society lost a heap of highly advanced technology? How do you work your way back up to it? Especially when you've got a cult like the Mechanicum in the way. It would be great to see, with what knowledge you have, to what level can you get your society? What a question. Anyway, I'm back with the Outer Circle. Thank you all for watching this completely out-of-the-box episode. If you like it, maybe I'll create more like it. If you don't, hey, just click the dislike or just walk away. I don't really mind. And wait for some more 40k, 30k content to come out. And I'll see you all next time.